we're going to finish off Chapter 1 in this vodcast. So we're going to be doing sections 1.7 through 1.10. And in this section, in these sections, we're talking about some properties of fluids that may not be as familiar to you as the properties that we discussed in 1.4 and 1.5. So we're leading into some other properties that determine how fluids behave and that describe how fluids behave would be a better way to put it. So we need to examine what they look like and start thinking about fluids in terms of this behavior of continuum, which is basically, we can't look at one molecule, and we can't look, if we have a river flowing with fluid, we can't look at the entire river. So we have to look at a piece of the fluid. So when we talk about different fluids, we define them by their properties. Now, one thing that came to mind that may be of common interest to you when you start talking about the behavior of fluids is the weight of motor oil. So for example, you might use 5-weight 40 or straight 30-weight oil or something like this. And the lighter the oil, the first number tells you what its actual, it relates, it's an SAE number that relates to its density. And then the second number, if it's a bi-numbered oil, refers to how it protects. Because heavier oils tend to protect engine components better, lighter oils are easier to move. So in the summertime, you may need a little heavier oil than in the wintertime. In the wintertime, when it's very cold, the oil will become more viscous and it will move less efficiently in your engine parts. However, too thick of an oil, too heavy of an oil takes gas mileage, so lighter weight oils are easier to move, and more of the energy output of your engine is deliverable to your drivetrain rather than lubricating the engine and turning the engine itself. So when you see something like 5-weight 40, that means one kind of a weight of oil, one kind of protection of oil, and straight 40-weight means something else. So there's a lot of different instances where we talk about the behavior of fluids, but that's just something that came to mind in terms of something that you may have seen in everyday life. All right. So going to the document camera, we're going to start with section 1.7 and start talking about the compressibility of fluids. The first thing about compressibility is that all fluids are compressible, but gases are much more compressible than than liquids. So if we talk about one of the terms that we can use to discuss the compressibility, when we start talking about it, is called the bulk modulus. And if any of you have had mechanics of materials, we've talked about this term a little bit in mechanics of materials when we start talking about solids. But basically, we use the abbreviation E sub V, and we say that the bulk modulus is minus the differential of pressure over dV over V. And basically, the V with a bar through it in this class refers to volume. So basically, we're talking about the change in volume per volume. So this is a dimensionless term. So it's basically how it's a percentage or a fraction or a decimal, really, of how volume changes with a change in pressure. Now, if you think about it, if pressure increases, what's volume going to do? It's going to decrease. And that is the reason for the sign of negative here. Now, we can also say that if we remember that density is equal to mass per volume, using the V with a cross through it like your authors do, we can also see that we could write this as d rho over rho, because the mass in both cases is going to be the same and it will cancel out. So these are just two mathematical expressions for how the volume of a substance changes in response to a change in pressure. So a lot of the compression and expansion ideas that we come up with are functions. Compressibility is a function of the fluid itself. And if we talk about the compressibility of gases, it could be a linear function For example, in the ideal gas law, if we have an ideal gas, we know that P times V is equal to mRT, or we can see that these two, if we have an isothermal reaction, M, R, and T are all going to be constant, so that means that P is inversely proportional to V. In other words, as P increases, volume is going to have to decrease. If we write P is equal to M over V RT, or P is equal to rho RT, we can see that for that same isothermal reaction, or isothermal process, that P over rho is also going to be a constant for an ideal gas isothermal process. And that's one type of a proportionality. Now, there are other types of processes as well that your authors talk about. They talk about one where if we have pressure over rho raised to some exponent, which is called K as a constant, that's what it kind of looks like for an isentropic process. And isentropic means that the entropy from one state to the next remains the same. Right? And that basically K in this particular case is the ratio of the specific heats, specific heat at constant pressure divided by a specific heat at constant volume. So you may remember some of that from chemistry. So we continue and we just kind of look at some of these different relationships in section 1.7. But basically, compressibility is pronounced for gases and less so for liquids. Okay, so we describe the compressibility based on some different relationship factors, and it may or may not be a linear relationship. So you have to define what the functionality is, what that functional relationship is before you can make that determination. And whatever you do, do not fall into the trap of assuming that every gas, or God forbid, every fluid is an ideal gas, because the ideal gas law only works for ideal gases. So that sounds redundant, but it's quite common to misuse that equation or that relationship. The next thing that we talked about is the speed of sound. And the speed of sound is a function of temperature and pressure, mostly, well, I won't even say that, but it's a function of temperature and pressure. And there are some relationships that talk a little bit about ideal gases, but the speed of sound is designated by the letter C, and that means the speed of sound. Now, the speed of sound is also referred to as Mach 1. All right. What Mach 1 is, a Mach number is a dimensionless number, and it tells you how fast something is going relative to the speed of sound. So if you are at Mach 1, that means you're traveling at the speed of sound. If your Mach number is less than 1, you are below the speed of sound. And if your Mach number is greater than 1, you are traveling faster or above the speed of sound. So if you take the velocity of your substance at the ambient conditions and divide it by the speed of sound, that will give you the Mach number. So you can see you have a velocity divided by a velocity. Now, the speed of sound is somewhere in the vicinity of 950 feet per second, more or less. But it depends on the conditions in the atmosphere, the temperature and the pressure. So for an ideal gas, it can actually be computed as the square root of that ratio of the specific heats times the ideal, or times the universal gas constant, or the gas constant for the particular substance, times the temperature, and take the square root of that. But just suffice it to know, if you look at that, that's a strong function of temperature. So C is actually proportional to T to the 1/2. Okay, but anyway, so this is actually a really interesting effect, in that prior to World War II, it was sort of a goal to get supersonic aircrafts. And it was found that there's a change in the relationship of the way that fluids behave right at Mach 1. So when you're when you're traveling subsonically or supersonically, there are some shock waves that are set up right at Mach 1. And what happens because of that is passing through the sound barrier presents some unusual effects. It has to do with the relationships within the fluid that you're passing through, which is generally air, but it also has to do with how the control surfaces of an aircraft respond to the air passing over them as the air changes. So anyway, a lot of times where pilots were trying to exceed Mach 1, they would actually go into a nose-first dive in their aircraft, and they would recover as they got closer to the ground sort of spontaneously, or it felt spontaneous, but really what was happening was the air was becoming denser, the temperature was changing, the speed of sound was changing, and the supersonic to subsonic nature of the aircraft was changing based on the change in the speed of sound. So that was actually conquered by creating some more moving surfaces on the tail section of aircraft. I mean, assuming that the aircraft was powerful enough to go Mach 1, they were able to learn how to control it later on. But there's some really interesting videos about that. If you're ever interested, I can give you some names of those things. But suffice it to say for now that the speed of sound is not really a constant, but is a function of temperature, and is sometimes a function of, well, this is for an ideal gas, so it's a function of the atmospheric conditions. Okay, in section 1.8, we talk about vapor pressure. And as you know, pressure and temperature have some functional relationships as well. But basically, suffice it to say, a liquid boils when the pressure is reduced to the vapor pressure. So if the pressure in a liquid is greater than the vapor pressure, it will not boil. But if the pressure in the liquid is reduced below the vapor pressure, the liquid will boil. And boil does not have to be hot. It can just be that phase change between liquid and vapor. And that's actually, it's defined as the phase change between liquid and vapor. So some fluids, water of course, if we're at atmospheric pressure, boils at 100 degrees centigrade. And if we decrease the pressure, it will boil at a lower temperature. So here in Powell, Wyoming, where we are at a higher elevation and therefore a lower atmospheric pressure, water doesn't actually boil at 100 degrees centigrade. It actually boils at a lower temperature. So vapor pressure is also, you need to remember that pressure is a function of temperature, and temperature then, well, I guess I want to say that the vapor pressure is a function of temperature, and so as the temperature, so you can say what a number is. You can say, what is the vapor pressure of water at 100 degrees, or what's the vapor pressure of water at a certain set of conditions. But it depends, it changes based on the ambient conditions. All right, and this is another thing that sometimes you'll see where if you have a pump that vapor locks, this is actually what's happening. If the temperature increases, you'll start to break, the boiling will start to happen. Boiling of that fluid will start to happen in a different way. Or if you're in a siphon tube and you create a low pressure region, you can actually start to vaporize part of your fluid due to that effect of going through a siphon tube as well. Section 9, we talk about surface tension, and this will lead us into the concept that we'll finish up with, which is capillary effects. All right. Now, surface tension is generally described as if you have a liquid, if you are to put a wire through that liquid and pull the wire up, depending on, I always think about this like one of those little things that you use to hold an Easter egg as you're dyeing it in a cup of dye. But basically, depending on the nature of that fluid, when you pull the ring up, the fluid will tend to follow the ring. And that is the surface tension of the fluid. Now, surface tension is a really interesting effect because it leads to a lot of other ideas. Some fluids have a high enough surface tension that they will bind to themselves. In other words, this is called a non-wetting fluid based on a different tube. But like mercury has a high surface tension. And if you spill mercury, if you have a container of mercury and you spill it out onto a surface, it will tend to ball up into little spheres of mercury because it preferentially adheres to itself. Now, there are other types of fluids or agents called surfactants. And surfactants, like soap, are different types of things that you can add to fluids to change the surface tension of the fluids. But one of the things that is a direct result of fluid tension, or surface tension, is something called capillary rise. And what this means is, this is actually the basis of manometry, if you remember from thermodynamics. But basically, if you have a capillary tube and you put an open end of it in a fluid bath, you'll see that the fluid in the bath will actually rise up in the tube or become depressed in the tube. So if the level of fluid is here, you can see that the fluid may be above the surface of the fluid, or I should finish that. It's not closed at the bottom, but it's just a little the end of the tube, or it may actually be below, depressed. And what that depends on is whether the fluid preferentially adheres to itself, which is called a non-wetting fluid, or if it preferentially adheres to the tube. So it depends on the nature of the fluid and also the substance that would make the tube out of. So if you have a glass tube with water in a clean glass tube has very little of this effect, and it has what is called a contact angle. If you observe the angle that you would create by extending this and this is referred to as the contact angle theta. The water in a clean glass tube is almost equal to 0 degrees, whereas mercury in a clean glass tube has a contact angle here to here of approximately 130 degrees. And those are sort of the two big fluids that we work with in terms of this effective capillary rise. But basically, it's caused by the surface tension. It's caused by how much this fluid prefers to wet to the surface of the tube or how much it prefers to not wet to the surface of the tube, but rather adhere to itself. So you can envision here that the mercury is attempting to form part of a sphered surface, a little ball of trying to gather itself up into itself. All right, well, if you take this shape, probably have heard this shape, is called a meniscus. Okay, so the meniscus is the curvature of that shape of the fluid as it rises in a capillary tube. And if you take the distance from the fluid surface to the meniscus, and there is some decision to make as to whether we're talking about where it intersects the tube or if we're talking about the top of the meniscus. And we are talking about the point where it intersects right here. Okay, so if you take that height, this of course would be a negative height, this would be a positive height. You can also, well, I won't get into that, but you can see from trigonometry that there's a change in the trig functions after you pass an angle through 90 degrees. So from 0 to 90, you have one sort of 0 to 90 contact angle, you have one sort of a wetting situation, and 90 to 180, you have a different sort of a wetting situation. But basically, we can use some values of the fluid, and this is on page 27 in your textbook, but we can calculate this value of H by taking 2 multiplied by the surface tension, which is going to be in units of force per length. We'll talk about that in a minute. I'll show you where to find these values. The surface tension times the cosine of that angle, which once again is going to be less than 90 for a wetting fluid and greater than 90 degrees for a non-wetting fluid, divided by gamma, which is the specific weight of the fluid. All right, and divide again by the radius of the capillary tube, and you'll get a height. The other thing you can notice is that, just not speaking of the fluid, but speaking of the tube itself, that the smaller the radius, the greater the height. So if you get a tube that is too thick, the height is not going to be as pronounced. So using the term capillary tube just means a narrow tube. And that's the reason, mathematical reason, that we use narrow tubes, because we get a more pronounced height if we have a smaller radius. All right, so I'm going to take a look at a problem for you. I'm going to do problem 187. And problem 187 states that we have an open, clean glass tube that has a diameter of 3 millimeters. It's inserted vertically into a dish of mercury, and the mercury is at 20 degrees centigrade. Okay, how far will the column of mercury in the tube be depressed? So that means we're looking for H, doesn't it? All right, so the height of that column of mercury is going to be 2 times the surface tension of mercury in a clean glass tube, times the cosine of the angle, which I've already told you between glass and mercury is 130 degrees. That data is easily found. It's easy to find. In your textbook, they state that on page 28. Just write this down. Cosine theta between mercury and clean glass tube is 130 degrees, and that's on page 28 of your textbook. But there are tables. You can go to a CRC table, or you can go to the internet and find those values as well. So continuing then, we have gamma on the bottom, which is that specific weight in newtons per meters cubed, times the radius of the tube. All right, so to find these values, we want to find surface tension of mercury, and we want to find gamma of mercury. Well, one thing we know about mercury is it has a specific gravity of 13.6, meaning that it is 13.6 times as heavy as water. So whatever units we need, we can multiply that by 13.6 if we have the value of water, and we can determine what that is. Now, a diameter of 3 millimeters means that we have a radius of 1.5 millimeters, and chances are we're going to have to convert that into meters. So a millimeter is 10 to the minus third meters. So that's also, we can express that as 1.5 times 10 to the minus third meters. All right, so where do we find a value for surface tension in your textbook? Well, if you look on page 26, it refers us to tables B1 and B2 for water. Okay, so those will be the appendices in the back of your book. There are also some values of surface tension of common liquids in tables 1.5 and 1.6. Okay, so let's take a look at your textbook and see if we can determine that value. We're interested in mercury, so let's see if we can find table 1.5, 1.6, and maybe on the inside front cover of your textbook. Yep, there we go. If you look at the values in the inside front cover of your textbook, you can find mercury, and it has a value, this is in pounds per feet. We probably would prefer to have it in metric units. Surface tension, I'm given a value of 4.66 times 10 to the minus 1. Oops, I got to pull this up here. 4.66 times 10 to the minus 1 in units of newtons per meter. Okay, so that's on the inside front cover of your book. So my surface tension of mercury is 4.66 times 10 to the minus 1 newtons per meter. And I wanted to show you that's what a surface tension looks like. And basically if you go back to that idea of pulling a wire through the surface of water, it's talking about how many newtons you have to pull with for a meter of distance. So obviously it's going to be quite tiny because there aren't very many fluids that are going to stretch a meter in that type of an operation. Okay, and basically, I guess I never really came out and said this, but surface tension, we talked about it with mercury, that mercury likes to form little balls, but basically the origin of surface tension is you have a container of liquid. The molecules up here above the container are vapor, and the molecules below in here are liquid, so these are more tightly spaced. Turns out that on the surface, that the molecules on the surface will be preferentially attracted to the liquid below, and to sort of make up for this deficit in attraction to what's going above, because there's just less stuff that will be preferentially attracted to itself. So you get this little bit of tension that is just like a film effect, where the molecules immediately on the surface prefer to be attracted to each other rather than to be attracted to the molecules above, mostly due to the fact that there's just more of them. All right, so continuing with that idea, the next thing we need to do is just find the gamma of mercury. Now we know that it's 13.6 times gamma of water, or we can go back to that same table in the inside front cover of the book where we specifically have a value for mercury. Here's density, here's gamma, mercury, 133 kilonewtons per meter cubed. 133 kilonewtons per meter cubed. And kilo is 10 to the third Newton per meter cubed. Okay, so now we've got all of our data. Let's plug it in and see what we come up with for a unit, or for units on our answer. So our H, or our capillary rise or depression is going to be 2 times the value for surface tension, 4.66 times 10 to the negative 1 Newton per meter times the cosine of 130 degrees. And we divide that by gamma in units, excuse me, the value is 133 times 10 to the third Newton per meter cubed times the radius of that capillary tube, which is 1.5 times 10 to the minus 3 meters. All right, so now before we get our number, let's work with this. Cosine is dimensionless, of course. Newton cancels Newton. Here we have a meter. Well, I guess if you think about it, this cancels this to meter squared on the bottom. So meter squared flips up here, and that cancels against this. So overall, the unit of H is going to be in meters. Okay? And is that a good unit for height? Absolutely. All right. Now, if you run through the numbers on this, the first thing that you may be aware of, if you can see that value, I don't know if you can see that calculator very well. Let's clear this. If you take the cosine of 130, we're going to find out, first of all, if we're in good units. I think I'm in degrees. Yeah, I am. It says my enunciate up there says I have a negative value. Okay, what that tells me mathematically is that any time that my angle, my contact angle, is greater than 90 degrees, I'm going to have a negative value, which means that I'm not going to have a capillary rise, but I'm going to have a capillary depression instead. So if I take that value, cosine of 130, and I multiply it by 4.66 times 10 to the minus 1, multiply it again by 2, divide that number by 133 times 10 to the third power, and divide it again by 1.5 times 10 to the minus 3, which is 1,000 on the top. I get a value of 0.003 meters, which is a tiny little amount of meters, but of course turns out that that is 3 millimeters. Now this value is actually negative, wasn't it? So my height, my capillary rise is negative 3 millimeters, which means we have a depression of 3 millimeters. All right. All right, so that's it for chapter 1. Chapter 10 just talks about some of the history of fluid dynamics and fluid mechanics. Fluid mechanics is really the principles, the physical principles of fluids. So far in chapter 1, we've really discussed more fluid mechanics. Fluid dynamics begins to talk about where the fluids are actually in motion, which is pretty interesting stuff as well. But if you read through section 1.10, you'll be introduced to some of the main scientists who have developed the sciences of fluid mechanics and fluid dynamics, which we also sometimes divide into hydraulics and hydrodynamics, where hydraulics is more the nuts and bolts empirical side of the science, and hydrodynamics is the differential equation side. But if you look at 110, there's no homework from that section, but it's kind of interesting, and you'll see the names of people for whom units are named in the field of fluid dynamics or fluid mechanics. So that's it for chapter 1. Your homework is posted to both Moodle and the wiki space. So when you finish chapter 1 homework, then hopefully I'll get some videos posted for chapter 2 very quickly. And after we finish chapter 2, we'll be ready for our first exam. Thanks. Have a great evening.